Chapter 11. This week we're going to talk about gas laws. Have you ever purchased a Mylar balloon and it's nice and tight and puffy in the store, and then you walk outside in the cold on a winter day and all of a sudden it just shrinks? Bring it back inside and it's back to normal. Did you ever wonder what causes that? Well, that's what we're going to talk about today. Exactly what is going on inside that balloon. So gases have been studied for ages. Back with Robert Boyle, he studied pressure changes with changes in volume. Jacques-Andre Charles, he examined volume changes with temperature, and that brought us to Amedeo Avogadro, who studied the relationship between the volume of gases and the volume of molecules of the gas. We studied Avogadro's number last week in laboratory. That was the 6.02 times 10 to the 23rd. Although many other studies have occurred over the years as well. So we look at an ideal gas. It's a model for gas studies. It consists of point-like particles that do not interact with one another. Particles fly in straight lines until they collide with something, and collisions are elastic. No energy is lost. So as you can see, the gas in this box, they're bouncing off the sides of the walls, but they keep moving. This is simply a model. It doesn't include any of the attractive forces that we've talked about and could never form liquids or solids at any temperature. Under normal conditions, this model proves to be very close to reality. An ideal gas is an approximation for a real gas. So why is it never reasonable to ignore intermolecular forces in liquids and solids? Well, in liquids and solids, the molecules are packed very tightly together and possess a very low kinetic energy. They're not moving around anywhere near as fast as what they would be when they're a gas. There are four variables that we use to describe an ideal gas: pressure, volume, the number of moles, remember mole is 6.02 times 10 to the 23rd, and temperature. Familiarity with these variables allows us to understand the ideal gases. So let's talk about atmospheric pressure first. This is air pressure, or the force that's exerted in the air around any object. You can see the air pressure being forced upon this can. When the can is filled with air, molecules batter the outside and the inside of the can equally, and there's no pressure. When air is pumped out of the can, we see that it shrinks, and with no opposition from the inside, the pressure exerted on the outside air crushes the can. Next is pressure. The definition of pressure, and this is important to remember, is the force per unit area. We usually measure this with a mercury barometer. You may have heard your meteorologist talk about the barometric pressure outside. This is the air outside the tube pressing down on mercury, and it pushes the mercury up in the tube. Normal atmospheric pressure is 760 millimeters of mercury, and that is the distance that the mercury travels up the tube. We call 760 millimeters 1 atmosphere of pressure. You are going to have to be responsible for knowing that 1 atmosphere of pressure is 760 millimeters of mercury. There's other variables that are easily measured. The volume of the container that contains the gas. This must be in liters, not milliliters, but liters. We'll have to convert it if it is in milliliters. The temperature can be measured with a thermometer. We always use Kelvin with ideal gas laws. Remember, Kelvin is the degrees in Celsius plus 273.15. And the number of moles. This is the number of gas molecules present. We know that 1 mole is 6.02 times 10 to the 23rd atoms. So here's an example. An empty half-gallon milk carton sits in a room where the temperature is 25.2 degrees Celsius. The barometric pressure is exactly 1 atmosphere. What is the Kelvin temperature? What is the pressure in millimeters of mercury? And what is the volume in liters if 1 gallon is 3.78 liters? Pause here, see if you can figure these out, and hit play to see the answer. Okay, the temperature in Kelvin is 25.2 degrees Celsius plus 273.15. That gives us 298.35 Kelvin. What is the pressure? Well, we told you it was 1 atmosphere, and 1 atmosphere is 760 millimeters of mercury. Now to figure out the volume in liters, remember it has to be in liters. So a half a gallon times 3.78 liters per gallon, and gallons cancel out, gives us 1.89 liters. So we're going to start working on the ideal gas equation. This is the mathematical relationship between the variables that describe a gas. First, we'll describe it in words, then we'll look at the math. Okay? First is pressure. That represents the number of collisions between the gas molecules and the container walls. You can see that happening with this molecule or atom inside this box. Then we're going to explore the pressure of a gas. We're going to look at what happens to the pressure when we adjust the volume. We're going to look at what happens to the pressure when we adjust the temperature. And we're going to see what happens to the pressure when we adjust the amount of gas. So starting with what happens to the pressure when we adjust the volume. As the volume of the box gets bigger, the pressure on the walls decreases. The pressure is inversely proportional to the volume, and the pressure is proportionate to 1 divided by the volume. Second, what happens to the pressure when we adjust the temperature? Well, we kind of discovered this one with the balloon example in the beginning. As the temperature of the box increases, the pressure on the walls increases. This causes, and the molecules are moving faster, and it actually increases the volume. So what happens to the pressure when we adjust the temperature? Well, as the temperature of the box increases, the pressure on the walls increases. So pressure is directly proportional to the temperature, as in the balloons, right? So what happens to the pressure when we increase the amount of gas? So what if you were to take that balloon and add more helium to it? Well, as the amount of gas in the box increases, the pressure will increase as well. As you can see, we increased N. N is the number of moles. We've got more in there now. All right, so what happens to the pressure when we increase the amount of gas? Again, as the amount of gas in the box increases, the pressure on the walls increases. So that means pressure is inversely proportional to the number of moles. So here's a summary of those relationships. Pressure is proportional to temperature, pressure is proportional to the number of moles, and pressure is proportional to 1 over volume. So combining these, pressure is proportional to NT over V. So when we convert it to math, pressure equals the constant times NT over V. The ideal gas constant, and you have to memorize this, is 0.0821 liters times the atmosphere over Kelvin times moles. But the 0.821 is what you're going to have to memorize. So the ideal gas equation can be found here. But this is the one I want you to really memorize. PV equals nRT. And it's kind of nice because it rhymes. PV equals nRT. So we're going to be able to solve for any part of this gas law if we know all of the parts. If we know everything but P, we can figure out P. If we know everything but N, we can figure out N. So how would you find the pressure of an ideal gas with these conditions? If N is 0.1 moles, the volume is 2 liters, and the temperature is 600 degrees Celsius. Okay, how do we do that? We have everything we need because we know the constant, which is R. So we just fill everything in and solve it algebraically. First, we have to convert that temperature to Kelvin. Remember, we have to use Kelvin. Kelvin was the temperature plus 273.15, which brings us to 873.15. Now we're going to plug this in. Okay? So in order to solve for pressure, we have to divide both sides by volume. So now volume is on the bottom. So P equals nRT over V. Plugging in our 0.0821 times 0.1 moles times our Kelvin divided by 2 liters gives us 3.6 atmospheres. So using that ideal gas law, we just solve for much more than PV, N, and T. We can often find values related to those variables, such as the molecular mass, densities, and other variables. We also have initial condition, final condition problems. These are problems in which one or more variables might change. It's solved by placing initial conditions equal to final conditions. So how would you find the final pressure of a cylinder filled with gas at an initial temperature of 200 degrees Kelvin and a pressure of 5 atmospheres. And then all of a sudden we heat that sucker up to 400 degrees. What is going to happen? What is our new pressure? So we are trying to solve for the final pressure here. So we're going to use these relationships, but we can remove those constants since we don't need them. So we're going to fill everything in and solve for PF. So next we rearrange to solve for the final pressure and substitute in the other values. The final pressure is 10. Here's a quick initial condition, final condition, gas problems step chart for you to refer to in the future. So let's look at standard temperature and pressure. This is usually defined as 0 degrees Celsius or 273 Kelvin and 1 atmosphere of pressure. When we look at molar volume, this is the volume occupied by 1 mole of gas at standard temperature and pressure.